Okay, let's take a look at our quiz. Okay, so the first question for the quiz is, consider the function f of x equals x times 1 plus x squared to the negative 2. Find a power series centered at x equals 0 for this function. And hint, first find the integral of this function. Okay, so were you guys all able to integrate x times 1 plus x squared to the negative 2? Hopefully you were. So let's take a look. So if we want to integrate that, so we're integrating x over 1 plus x squared to negative 2 dx. So what's the easiest way of integrating this? What's the first step? Yeah, it's just a u sub. And I'm going to save some time. Because it's really an easy u sub. U equals 1 plus x squared, d equals 2x dx. We have an x dx, you get a half. So notice that we get 1/2 times the integral of u to the negative 2 du. And that is equal to, well, the integral of u to the negative 2 plus 1 is negative 1. So we get negative 1/2 times u to the negative 1, which is the same thing as 1 over 1 plus x squared. Okay, there's a plus c. Because we're going to be taking a derivative later, we don't need the plus c. But if you want to stick it there, you can. Any questions on the first step? Okay, now that we have that, hopefully you all know how to take negative 1/2 times 1 over 1 plus x squared and turn that into a power series. So how do we turn that into a power series? Well, the negative 1/2 stays negative 1/2. Let me, just so you guys can see, let's copy and paste that. So that's equal to negative 1/2. And now we're going to have a summation. And how do we take 1 over 1 plus x squared and turn that into a power series? And the key is, at this point, we only have one kind of power series we know how to do. That'll change by later.
Make the plus x squared minus negative x squared.
Exactly. You do minus negative x squared, and then that is a geometric series with our r equals negative x squared. So we just have negative x squared to the n. Okay, and we're going from 0 to infinity, but that's just immediate. And it's nice to rewrite this as negative 1/2 times the summation of negative 1 to the n. This is just cleaning it up, times x to the 2n. Any questions on that? Okay, now remember, let me remind you, that was the integral of f of x dx. That's not f. Okay, we want the power series for f. Well, if we know the power series for the integral of f, how do we get the power series for f? Yeah, we just take a derivative of both sides. The derivative of the integral of f of x dx is just f of x, right? So that's important. That happened last quarter, actually. So now what I'm going to do, let me copy and paste. And let's adjust. So we don't need these middle steps anymore. The derivative of the integral is the function. And then the derivative of negative a half, the summation negative 1 to the n, x to the 2n. It looks really nasty, but it actually isn't. I guess I should leave the integral for now. Yeah. Okay, so that tells us that f of x is equal to, well, how do we take the derivative of a power series? And it's really easy. That's a hint. What happens to the x to the 2n? Everything else is just a constant. So what is the derivative? I'll start you out. It's a summation. Yeah, the x to the 2n becomes close. It's not quite 2n x to the n. Remember, when you take a derivative, you're subtracting 1. You're not dividing by 2. Yeah, it's going to be 2n x to the 2n minus 1. So, and notice that the 2 and the 1/2 cancel. We could take that negative and put it in the negative 1 to the n and make that negative 1 to the n plus 1. Again, the 2 and the 1/2 cancel, so no more 1/2. And we just have x to the 2n minus 1. Any questions on that? Okay, nothing, in terms of the derivative rule, there's nothing fancy here. It's a derivative of power. Subtract 1, and that's it. And pull the original power out. I lost the n, sorry. So there's an n right there. Any questions on that? Okay, let's look at question 2. Question 2 is evaluate the series of summation n equals 1 to infinity of n over 3 to the n by considering it as f prime of 1/3 with f of x equals n equals 0 to infinity of x to the n. Okay, so that's the first thing we have to do. So we have this summation, and this is very simple. How do we find the derivative of a power series? Just use the power rule. So let's take the derivative. So we know that f prime of x is going to be the summation of n, x to the n minus 1. And by the way, when you're taking a derivative, when you're doing with derivatives, you need to start at 1. That's a minor thing, though. Any questions on that? Okay, and what happens when you plug in a third? That was a big hint. So let's plug in a third. So f prime of a third is equal to the summation of n times 1/3 to the n minus 1. Any questions on that? Okay, nothing fancy here. Okay, so now let's see what we got. So that's what we got, and let's see what we want. What we want is n over 3 to the n. Now, we don't have n over 3 to the n, do we? How do we make this n over 3 to the n? What can we do to make that n minus 1 an n?
Derive it again.
Write it again? Maybe, I'm not sure what you mean by that, though.
Oh, wait, never mind. No. All right, integrate.
Don't want to do that. It's really easy. That's a hint. All I do is I'm going to multiply by 1/3. And then I'm going to also multiply by 3. You're always allowed to do that. That's just multiplying by 1. Any questions on that? Very simple, but you have to know what to do. Okay, it's a very simple math trick. Whenever you don't have something, you put it in there, and then you have to adjust for what you put in. And then now we're looking at 3 times the summation. Let's write this out. This is equal to 3 times the summation, and now the n minus 1 becomes an n. That was the whole point. And that is equal to 3 times the summation. I can rewrite all this as n over 3 to the n. And that's what I want, right? That was the original question, was the n over 3 to the n. Any questions on that? Okay, but now we need to do a little more. We have f of x equals the summation n equals 0 to infinity. What's a nicer way of writing f of x? How do you realize the summation n equals 0 to infinity of x to the n? What kind of series is that? Starts with a G.
Geometric?
Yeah, that's a geometric series. So we can now say that our f of x, let's do it. Our f of x now is equal to this series, which is also just 1 over 1 minus x. That's geometric series, standard geometric series, nothing even fancy there. So f prime of x, well, how do you take a derivative of that? Okay, in fact, you might want to rewrite that just to make it easier to see a derivative, is 1 minus x to the negative 1. Might be easier to think about it as a derivative. So now what is the derivative of 1 minus x to the negative 1? That's supposed to be easy. I don't see y'all jumping in. So negative 1 minus x to negative 2, close, but there's actually 2 negatives that come out. There's the negative from here when you do the power rule, but there's also the negative here when you do the chain rule. Does that make sense? So you actually negative 1 minus x to negative 2, which is just 1 minus x to negative 2. So again, everything comes back from the last couple quarters. You got to know how to integrate, you got to know how to take derivatives. It just happens. So there's f prime of x. Well, f prime of a third, you just plug in a third. What's 1 minus a third? That's supposed to be easy. 1 minus a third.
2/3.
Yeah, it's 2/3. What's 2/3 to the negative 2? Remember, negative takes a reciprocal, right?
9/4.
Yep, so we know that f prime of a third is 9/4. So let's write down. We're getting there. Okay, but f prime of a third is 3 times what we want. So how do we get what we want?
Divide by 3.
And that gives you 3/4. So what that tells us, one more time. Is our sum that we want is equal to 3/4. Because I have to divide by 3. Okay, part B is actually really quick. So let's read part B again. Explain what's wrong with using the function f of x from part A and the corresponding series to express f prime of 3 as a series. Okay, what's wrong with plugging in 3 into this and doing the same thing? Because we could just say, hey, 1 minus 3. 1 minus 3 is -2. -2 to the -2 is 1/4. And do the same thing. What's wrong with that? Anyone know it? What's the problem with it? The hint is it doesn't work, but why doesn't it work? This is the old, like, a few words and you're done with the whole problem. Any thoughts? Yeah, exactly. So by the geometric series test, 3 is greater than 1. Okay, and actually, I guess technically, but it works. It's really the absolute value of 3, because that's geometric series test, is greater than 1. Therefore, the series diverges. So you can't evaluate it. And that's it. Okay, it just, you can't do anything once you have a divergence series. You can't play any games. Any questions on the quiz? Any questions? Okay, it's getting pretty complex, and I guess I should warn you, this is the complex time of this whole class. Okay, it's beautiful, I think, but it is complex. There's a lot of summation signs, a lot of symbols, and you have to kind of figure out what to do. And that includes what we're doing just today also. Any questions before I move on to the big event of the entire quarter? Definitely the most important. I would say it's not quite as important, but pretty close to the fundamental theorem of calculus. The last quarter, the big event was the fundamental theorem of calculus. This quarter, the big event is what we're doing today. So any questions? Okay, if not, let's go for it. Okay, so now we understand how to find, or how to see a Taylor series. Sorry, a power series. And we also know that a power series is a function, right? So now what we want to do is we want to say, well, we have this new idea of these creatures called power series. We've known about functions forever. So can we take a function and realize it as a power series? Okay, does that make sense? And I think what I'm going to do is I'm going to do kind of a nice thing. We're just going to say, let's suppose we have a function. So let f of x be a nice function. Okay, and by the way, this year, not just this quarter, but the whole year, when we talk about being nice, what is it? What do I mean by that? What can we do with the function? This is calculus, that's a hint.
Integrate it.
Can integrate, what else can you do? Yeah, you can take a derivative, and in particular, we want to be a very nice function. So let me actually put the word very nice. Okay, these are my words. Very nice is not a math word, but let me show you the math words. That means that Fn so remember, that's not a power. That means the nth derivative of x exists for all n. So not only can you take a derivative, but you can take a second derivative, a third derivative, a fourth derivative, et cetera, et cetera, et cetera. Any questions on that? Okay, so let's suppose you have a really nice function. And I'm not going to get into the details because that's advanced math, but it's going to be a little nicer than I'm saying, but just a tiny nicer. It's really hard to come up with a function where all the derivatives exist and it's still not nice. So for us, just think about the derivatives all existing. Okay, and by the way, that covers most functions. Can you think of a function where the derivative, where you don't have an infinite number of derivatives at any point? That there's if I give you a value of x, no matter which value of x, you're not going to be able to find the derivatives. And it's hard to come up with one. And my guess is most of you probably won't be able to think of one. So almost every function you've ever seen in your life will work. Okay, but sometimes you have to make it, you can't let it be just at 0, you have to do a little shift. So just a note that functions are, just about every function we've ever seen is a nice function, nice enough. Okay, it may not be nice at a value, but it's nice somewhere. Any questions so far? Then let's look at the equation as follows. So f of x equals a power series. And I am going to just do it at 0. So I'll explain what that means later. A sub n, x to the n. Okay, and if I don't write anything, it means n equals 0 to infinity, by the way. That's just safe. Okay, so the idea here, our goal, is we have this function, and it's nice, and we want to write it as a power series. And what I'm going to do is I'm going to make a table. This is going to be kind of like a T table, but I'm going to make it an H table. You know what that means? So that means 3 columns instead of 2. So that makes it more of an H table. Something like that. I don't know if it's really H, but whatever it is. Okay, and what I'm going to have is I'm going to have n. I'm going to have f sub n, f super n, so the nth derivative of x. And then I'm going to have the nth derivative at a value, at a constant c, at 0 in this case. Any questions so far? And then we're going to see what happens. Okay, well, if n is 0, let's start with the easiest one. Then what is a sub n? What is f sub n? What is the zeroth derivative evaluated at, I don't want to be 0, at x?
Just f of x, right?
Yeah, the zeroth derivative is just f of x, okay? So the zeroth derivative is just going to be this guy. Is that clear? Okay. People don't even usually say zeroth derivative because it's just f of x, but it helps to see it. It helps for what we're doing. If I plug in 0, what do I get? The hint is it's really easy. Don't get 0. Remember that n starts at n equals 0 to infinity. If I plug in 0, what do I get? So the idea is all the x's become 0, but the very first term is just a naught. There's no x on the first term, right? Because x to the 0 is 1. That was our definition. So what we can say is that if I plug in 0 for the 0th term, I end up getting a naught. Any questions on that? Let's go for 1. If n is 1, what do I get? Well, that means I take a first derivative. If I take a first derivative, I get n x to the n minus 1. Okay. And here I probably want to remind you where it starts and ends. This is n equals 0. N equals now 1 to infinity. Remember, when you take a derivative, you raise by 1. Okay, now if I plug in 0, sorry, if I plug in x equals 0, what do I get? That is a naught. If I plug in 0, what do I get? Okay, not quite an n. The idea is, for example, if n equals 5, the a5 goes away. Which one doesn't go away? So the idea is the only one that doesn't go away is the n equals 1 term, because then you get an x to the 0, and that's just 1. And if n equals 1, I get a1. Have I lost anyone there? The idea is every term goes away except for the first one. And we're going to see a pattern about this pretty soon. And n equals 1, by the way. If n equals 2, you may guess you get a2, but we don't. Let's take a look what we get. So now if we take a derivative again, now we're going to start n equals 2. When you take a derivative, you always go up 1 on what you're starting at. And then we're going to have n times n minus 1, x to the n minus 2. That's just taking another derivative, right? If we plug in 0, what do you get? And this is where things get interesting. Not hard, just interesting. So if x equals 0, what do you get? And the hint is only the n equals 2 term is left. So what do you get if x equals 0 now? I don't see y'all jumping in, but this is pretty important, and this is the one where it gets more interesting. Then after that, you should be able to get all the rest easily. Hopefully. So what do you get if x equals 0? So that means that as long as n is not 2, as soon as n gets bigger than 2, it just zeroes out. So all you have is the n equals 2 term. And what do you get if n equals 2?
A sub 2 times 2.
Good. But I'm going to write it as 2 times a sub 2. The same thing. Any questions on that? Okay, now let's do the 3 term. So now we're going to have starting n equals 3 to infinity. And now we're going to have n minus 1 times n minus 2. Times x to the n minus 3. And what are you going to get now if x equals 0? And the hint is all you're left with is the n equals 3 term. And what do you get? So now what do you get if x equals 0? So if x equals 0, then as soon as n equals 4 or higher, the zeroes out, but the n equals 3 does not zero out. So that means just plug in n equals 3. And what does that give us? Okay.
6a sub 3.
Yeah, but it is true it's 6, but it's better if you elongate it out. So we're gonna have a sub 3 times 2 times 1, or 3 times, so 3 times 2 times a sub 3. Any guess if n equals 4? I think I'm not going to write it all out, but any guess what you're going to get if n equals 4? The hope is you might see the pattern now. If n equals 3, you got 3 times 2 times 1. A little more than 4 times 3. Notice you'll have a 4, a 3, and then you'll have the next one also. Do you see that? 4. Times 3 times 2. And if you want times 1, but I usually leave that one blank, times a sub 4. How about n equals n? Any guess on what you're going to get if we're looking at the nth term? And this is the biggie. And hopefully you see the pattern. The hint is there's fewer symbols. Yeah, it's going to be n factorial times a sub n. Any questions on that? All right, so what we want is we want to make sure that it works. So if we just let it be kind of if we just let it happen, then it wouldn't work because we're missing the factorial. Does that make sense? So here's the big theorem. This is how you put the factorial in and the derivatives. That's what we're doing. We're doing the derivatives. Each term is the derivative. Okay, so notice that it out. The nth derivative at 0 is equal to n factorial times a sub n. That's the whole point. Okay, so it's good to write the conclusion. And now I can do very easy math. And this is like one of the most important theorems of all of calculus. And this is the whole proof. There's nothing to it. And that is that a sub n is equal to the nth derivative at 0 divided by n factorial. And it is way too important to have it on 14.5. So that's huge. Okay, this is basically the big theorem, and now let's put it together to make it look like a series. So now I'm going to put everything together, and let us this is the big theorem, and this is called the Taylor series. And let f of x I'm just going to say be nice. So that means all the derivatives exist, and it's a tiny bit nicer that you won't even understand if I talked about it. So if the f of x be nice, then f of x is equal to the summation, and if I don't write anything, it means 0 to infinity, of the nth derivative evaluated at 0 of f divided by n factorial times x to the n. So that's just putting together what we just, x to the n. And again, way too important to be such a small point font, because this is the biggie. This is called the Taylor series, and it's used a lot. Any questions at all on this big theorem? I'll even put it in red, it's that important. Any questions? Okay, I haven't been proving a lot of theorems in this class, but this one was so important it had to be proven. Okay, so the proof was the table. That's all it was. So it was an easy proof, and there it is. Okay, so I think it's very important to think about, well, how do we use this, or what can we use it on? So what's the nicest function that isn't just a polynomial in calculus? Because polynomials are already written as a summation of something to times x to the n. What's the nicest function that isn't already a polynomial? Yeah, e, but not really e to the x is what you meant, right? Okay, I think e to the x is nicer than ln of x. One thing ln of x has trouble at 0, and I'll talk about that and what to do with ln of x. But e to the x is definitely the biggie. So let's do e to the x. And not only that, e to the x is so easy and wonderful. Okay, and I think you'll agree in a moment. So what I'm going to do is I'm going to draw my h table. And I don't need to actually do much on this one because it's so easy. Probably that's enough on this one. So we're going to have an n. We're going to have an f n of x. And then we're going to have an fn of 0. Okay. And I want to let you know, this particular example, you probably wouldn't have to do the table because it's that easy. But I want to show you kind of the fact that on anything that's anything more difficult than e to the x, you want to do a table. Okay, so that's right. If n is 0, then what is the 0th derivative of e to the x? It's very simple. Yeah, it's just e to the x. And if I plug in 0, what do I get? What's e to the 0? 1. Okay, if n is 1, what's the first derivative of e to the x?
E to the x.
E to the x. And if I plug in 0, guess what I get? 1, right? Usually you do more than just 0 and 1, but this one's so obvious, I hope. What's going to happen at 2 or 3 or 4 or 5 or n? What's the nth derivative? E to the x, okay? So this is the easiest example in the world, right? When it comes to non-polynomials. And if I plug in 0, guess what? I get a 1. Any questions on that so far? So now what I can do, I'm going to copy and paste the big theorem. And then I'm going to substitute. So first thing, this is a theorem. We don't need it in red because it's not the theorem now. Now we're just doing it. Come on. There we go. And we don't need it so big either. Okay. So now our f of x now is just e to the x. And fn of 0 was 1. Typically for this example, because it's so important, everyone writes it as x to the n over n factorial. This one's important enough, I think I want to make it a little bigger. Okay, this is a major, major important step in understanding functions. So what it means is that e to the x is just x to the n over n factorial. And we can look at that as kind of a power series, which is just one very, very long, infinitely long polynomial. Any questions on this example? Okay, what's the next most important that you would consider power series? Functions that isn't just a polynomial. Okay, I'm gonna do sine because you said it first. You said sine, okay, sine, but I'm gonna go with sine. So let's try sine of x. I think I'm running out of page, no, I have lots. So let's try f of x equals sine of x. Okay, just a note, by the way, what do you think the hard part is going to be? This was a really easy example, by the way. What do you think the hard part's going to be in writing down the Taylor series? There's two possible hard parts. And this one is going to have one of the hard parts. What do you think where's the challenge going to be? I made it look so easy, didn't I? Any thoughts? All right, if you're not coming in, let me explain one. Let's suppose we had, I don't know, how about x plus 1 over x squared minus 7? Imagine taking derivative after derivative after derivative forever. Okay, every single time you're going to have to use a quotient rule, and it's going to get messier and messier and messier. So one challenge is the derivatives are not always so beautiful like e to the x. Okay, now with sine of x, derivatives are beautiful. The other challenge, or we're going to see on this one, is how do you come up with a nice expression for the nth derivative? How do you see the pattern and write it out? And we'll see that happen in this example. So what I'm going to do is I'm going to make an H table. I'm going to make it a little longer this time. So again, we have an n. We have an nth derivative at x. And then we also have the nth derivative at 0. And if n is 0, then you just get f of x. That's just sine of x. Hopefully you get that when n equals 0, you just rewrite your function. But it's worth doing. What's the sign of 0? You all better know. 0. Okay. If n equals 1, what's the derivative of the sine of x? You all better know that one too. Yeah, that's the cosine of x. And what's the cosine of 0? 1. If n equals 2, what's the derivative of the cosine of x? Negative the sine of x. And if you plug in 0, you get 0. If n equals 3, then what's the derivative negative the sine of x? Negative cosine of x. And if you plug in 0, you get negative 1. If n equals 4, and this is important, what's the derivative of negative the cosine of x? The sine of x. And what's important about this, because it's going to happen a lot, is we're back. Okay? So then we have a 0. So notice that it took 4 times to get back to where we started. Do you see that? So we can say that we have a periodicity of 4 in terms of our nth derivatives. It takes 4 to get back. If I do 4 more, I'll be back to the sine of x. 4 more again, we'll be back to the sine of x. So in particular, now I'm going to skip the middle step because I can just say that's going to be a 0, 1. 6, 0, we're going to be at 0. And then you can keep going forever and ever and ever. Any questions on this? Okay. One thing that's very important to notice is that where do the zeros occur? What values of n do the zeros occur? Even, exactly. And in particular, it's not 0 for the odds. So here's a nice little definition. I'll just pop this in. Is that, and this is a definition, you've heard the word before, but you define it differently, but this is a better definition than you've seen before. That is f of x is an odd function if its power series has non-zero terms only at the odd powers. Then we have an odd function. And by the way, I'll just type it out now, even though I didn't do the example. But f of x is an even function, okay, if its power series has non-zero terms only at the even powers. Okay, so this is a different way of thinking of odd and even functions. You probably thought about it using symmetry and stuff. This is actually a better definition. Okay, so, and this will always work as long as you have a nice function. Any questions so far? Okay, so now we go back. And the first thing is, how do you write an odd number? What's the general way of writing an odd number? And I don't want the letters ODD, by the way. What are odd integers? If you want to write an expression for all odd integers, what do you write? In terms of n.
2 times n plus 1.
Good. 2 times n plus 1. And by the way, you have two choices, 2 times n plus 1 or 2 times n minus 1. I'm going to use 2 times n plus 1. So the first thing is you only have to worry about the 2 times n plus 1. Okay? So that means that the power of x is going to be 2n plus 1. Then we look at our derivative at that value and notice it's an alternating series. 1, -1, 1, and then the next will be -1, 1, -1, 1, -1. Any questions on that? So now what we can do is we can say that our series for the sine of x is equal to the summation of, plug in the formula, and we're going to have a -1 to the n that's alternating over 2n plus 1 factorial times x to the 2n plus 1. Make it bigger. Any questions on how I came up with this? Any questions? And what this does is it makes it so that there are no even powers of x. Do you see that? And in Taylor's theorem, in the formula, this n and this n always have to match up. So those two n's have to match up. So if you see an x to the n, you must have an n factorial. If you see an x to the 2n plus 1, you must have a 2n plus 1 factorial because they have to match. The numerator is the formula that works. And in this case, as you go back and forth from odd to next odd to next odd to next odd, it's alternating. And alternatings are by -1 to the n power. Either n or n plus 1. And since we're starting at 0, then, and we want to be positive to start, it's -1 to the n. Anybody lost on the derivation of sine of x? Okay, what's the next one? What's the next most important? After sine of x. Yeah, cosine of x. Okay, again, this wasn't a trick question. After you say sine, you should just be used to saying cosine. That's good. Let's go after x is cosine of x. And this one I can do quicker because it's going to look just like sine of x. So I'm going to make a table. Pop some in. And we have n. And then we have f super n of x. And then we have f super n of 0. If n equals 0, then you always write the irregular equation, just the original, and that's just cosine of x. If you plug in 0, what do you get? One. If n is 1, derivative of cosine is negative sine of x. And if I plug in 0, I get 0. Okay, if n is 2, what's the derivative of negative sine of x? Yeah, negative cosine of x. And if I plug in 0, I get -1. Now let's plug in 3. I'm going pretty quickly because hopefully you're seeing it's very similar to the sine of x function. If I plug in 3, derivative of negative cosine is the sine. And if you plug in 0, you get 0. If I go to 4, then the derivative of sine of x is the cosine of x. And if I plug in 0, I get 1. And notice I'm back where I started, right? I had cosine of x. After taking 4 derivatives, I'm back at cosine of x. So this has, again, full periodicity 4. And also, is this an odd or an even function? Or neither? Is cosine x odd, even, or neither? Yeah, this one is an even function because notice that all of the odd guys are 0 and only the evens are non-zero. This is also an alternating series, 1, -1, 1, it'll be -1, 1, -1, 1. But now it's an even function. So instead of a 2n plus 1, we're going to have a 2n. So I'm actually just going to copy and paste because it's a whole lot easier. Because it's really similar to the sine. And we could say the cosine of x is equal to -1 to the n over 2n factorial x to the 2n. And that's it. Was that too fast, or do you see that it's basically the same as the sine? Same ideas. Okay, what's the next most important function? that is not a polynomial. And it might even be more important than either the x sine or cosine. If you're not thinking, maybe I'll put it in. Tan's not more important than sine and cosine, that's for sure. So I think you'll agree when I write it down. How about f of x is equal to 1 over x? That's a pretty important function, isn't it? Don't you agree that that rivals sine of x, maybe even more important than sine of x? It's not a polynomial. What's its problem? Why is this going to cause issues? Yeah, if you plug in 0, it doesn't work. So here's what we're going to have to do. We're going to have to take our Taylor theorem and we're going to have to adjust it. And what we're going to say is that f of x now is not f super n of 0. It's going to be f super n of some number c. That's not necessarily 0. And then we're not going to have an x to the n. We're going to have an x minus c to the n. And that is going to be the Taylor series centered at c. Let's make it so it's on one page. Any questions on that? Okay, just a note. This guy is also called the Maclaurin series. So if you're centered at 0, this guy Maclaurin, I guess he did a bunch of stuff too, so they wanted to name something after him. So that's a note. If you hear about Maclaurin series, that just means centered at 0. Whereas Taylor series can be centered anywhere. Any questions on that? So if we wanted to do 1 over x, if we want to do 1 over x, we can't center it at 0. Where do we center it instead? What's the next best place? Yeah, 1. So we can center at x equals 1. And then we could do the same thing. I make my table. And we're going to have n. We're going to have the nth derivative. But I'm not going to write fn of 0 this time. What am I going to write now? The hint is nothing extra fancy, but yeah, it's fn of what? Yeah, of 1. So there's nothing new about this. That's just a note. It's not really that different. Just plug in a 1 instead of 0. You could choose whatever number you want. You could center it anywhere you want. So if n is 0, we have 1 over x. And then if I plug in 1, I get 1. If n is 1, you get negative x to the negative 2. And if I plug in 1, I get -1. Then if n is 2, I get 2x to the -3. And if I plug in 1, I get 2. If n is 3, I get 2 times negative, let me write it out. I get -2, let's go 3 times 2, because it looks a little prettier, x to the -4. And if I plug in 1, I get -3 times 2. Why am I writing -3 times 2 instead of -6? This is actually really important. Yeah, I want a factorial out of this. Okay, so if n is n, what I get is, well, it's going positive, negative, it's going negative, positive, etc. Right? So actually, I don't need it here. I need it here because now we're looking for the pattern. So it's positive, negative. So I get -1. It's alternating. -1 to the n, and then times n factorial. Any questions on that? All right, now we can put it all together. So now what I can do is I can say that 1 over x, one more time. 1 over x is equal to the summation of, well, what do I have? I have a -1 to the n times n factorial over n factorial. The n factorials are gone. So I just get -1 to the n times x to the n. Sorry, not x to the n, it's x minus 1 to the n.
Is it x minus 1 because it's centered at 1?
Exactly.
Okay.
Yeah, centered at 1, you always do x minus whatever it's centered at. I know there's a lot of 1s in this example. You can lose where the 1s are coming from. Now, this shouldn't be too big a surprise. How come? That this is what we get. How else could we have done this problem? Here's a hint. One over x is equal to?
Harmonic series.
Yeah, 1 over 1 minus, and then I can write, so we want an x minus 1, right? X minus 1. X plus 1, sorry. 1 minus a negative, let's get this right. So it's 1 minus, it's -1 over 1 minus, see if that works. No, but we can rewrite this as a 1 minus x minus 1, but it's 1 minus a negative x. There we go. So it's 1 minus a -1 times x minus 1. You have to play around with it to make it work. Hopefully that one works. 1 minus 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 minus, yeah. Does that make sense? And that's a harmonic series, and that's what you get. All right, and that's a tricky way of doing it. It's a lot faster than the table, but this one works with harmonic series. But the point is, you never have to use a harmonic series, but harmonic series is usually easier. Any questions on that? Okay, I have the last couple things to do. Okay, I spent most of the time on this because this is the biggie, but I want to show you my agenda, what else we have to do. So I just did examples, and that was most of the day. So the remainder theorem. So here's an example of thinking about the remainder theorem. Let's suppose we want to approximate E. So we know, by the way, that E now is going to be equal to the summation of x to the n over n factorial, but x is 1, so it'll just be 1 over n factorial. And we want to approximate it, and let's say you wanted E to 10 decimal places. How far do you have to go? And the nice thing is factorials get big really fast. 10 decimal places sounds like huge, but factorials, it doesn't take long to get 10 decimal places. So here's the big theorem. Okay. What it says is the following. The remainder, when approximating a Taylor series with a Taylor polynomial. When I say Taylor polynomial, what do you think I mean? What am I referring to? What's the big difference in a series and a polynomial? There's really only one difference. It's important, but it's just one small difference.
Polynomial goes to a limited amount of terms, while a series goes to an unlimited amount of terms.
Exactly. In the summation, with a series, you go up to infinity. And with a polynomial, you stop at 10 or 30 or 100, but you stop at a number. Okay? So if we're going to stop at a number, then the question is, what is the remainder? What's your error? Does that make sense? At stopping at a number and saying, I'm going to ignore the infinite number of terms. I'm going to stop at 100, for example, or something like that. So the key is this remainder is equal to the value of the nth term, n plus 1 term, sorry, let me write degree n, sorry. So in other words, we're going to stop at n, and we take the value of the n plus 1 term, evaluated at some x between c and the value you're interested in. Okay, so let me explain what that means. So what that says, for example, let's take a look at the e to the x one. Okay, let's look at e to the 1. So remember, we know that e is the summation of 1 over n factorial, right? So what this says is that if I instead stop it, not at infinity, but stop it at some number, then what we can say is the remainder in approximating E is going to be one over, and now we're going to have an n plus 1 factorial, because that's the next one. Times x to the n but I'm going to not call it x because that's what we're using as our variable, times, let's call it b to the n, or some b between 0 and 1. Okay, so the reason for that is if you look at the Taylor series for e to the x, and we plug in the next term, and you plug in b, that'll be the n plus first term. We don't know what b is. Does that make sense? We don't know what that remainder is, but there's some remainder. Okay, but we know that b has to be between 0 and 1. We don't know what the value is, but there's some value that'll be the exact remainder. So here's the idea, is that in particular, I'm going to copy and paste. I'm going to type again. The remainder, there's our remainder, is going to be less than, in this case, 1 over n plus 1 factorial. Because if b is between 0 and 1, then b to the n plus 1 is less than 1. So we know that we have this inequality. So if you want to go 10 decimal places of accuracy, then we just find an n such that 1 over n plus 1 factorial is less than 10 to the 10th power. And that might be 15 or something like that. You can go work it out in a calculator, and that'll give you e to 10 decimal places. And all you have to do is do, say, 15 different calculations, and you got a very serious, good approximation of e. Any questions on this theorem? Any questions? Did I lose you? Okay, we have 1 minute left to the last one. I said the last one's really quick and easy. Don't even need a minute, I don't think. And that is convergence. And here's what it says. It's a very nice theorem, but very easy. That is that if the Taylor series converges wherever x is nice, or up to where x is nice. So let me give you an example. Let's look at the tangent of x, because some of you said that that was the most important, one of the most important functions. Okay, I don't have time to show you the Taylor series of this, but you could do it. And that is its Taylor series, the Scopic-Lorentz series. Where will it converge? Up to where? Where does the tangent go bad? This is something you're all supposed to know. Where is a tangent bad?
Multiples of
Pi over
yeah,
2.
pi over 2.
Yeah, and in particular, you only have to worry about the first one you hit. After that, it's over. So it converges between negative pi over 2 and pi over 2. Okay. By the way, if we wanted it instead of the Maclaurin series, if we wanted to say the Taylor series at pi over 4, then it would be between 0 and pi over 2. So you go from center and you go out until you hit the first bad one. And then if you hit it on the left, you can't do more on the right either. Being on the right, you can't do more on the left. So that's the big convergence theorem. It means you don't have to do ratio tests and all that to find the radius of convergence because we have this big theorem. So hopefully you understand how important today was, because now it says that pretty much all functions can be rewritten as Taylor series. All right, so we're out of time. And next time would be our last day, by the way, and last day of new material. And what we're going to do is we're going to play with Taylor series.